Okay, good afternoon, everybody, and welcome to the fourth lecture. Um, so today, the lecture is going to be based a little bit on this PhD thesis by Cameron Bernice, but I'd say I'm just getting some of the very basic ideas. So his thesis is way more complicated. I just got some basic stuff. And again, just to remind you that the main reference on Unruh effect would be this one by Cristino, Higuchi, and Matsas. And today, after discussing briefly this circular motion in Minkowski vacuum, we're going to discuss a little bit about the protocol called entanglement harvesting. And I'd highly recommend this reference for this part. So let's get started. Oh, circular motion in Minkowski vacuum. Now, well, let's start off with a reminder that yesterday we had a very loose intro to Unruh effect, right? And one thing that we saw is that it's really hard to implement this experimentally, right? So basically not possible to experimentally observe. And the reason for that is because we need some huge, quote unquote, um, linear acceleration. And that should be for some arbitrarily long time, right? To be able to thermalize the detector. Okay, so the question would be, what if we consider circular motion instead? And yesterday, I gave you guys some homework because I told you that I wanted to start this lecture with some discussion. So the question would be, is this also over effect? So I want to get your opinions or pros and cons. What have you learned from a 5 minutes Googling yesterday about this topic? Please don't be shy. Okay, someone said something in the chat. Radiation is not thermal, but it's very similar. What else have you guys got? If you guys open your mics, maybe it's nicer, but I understand if you prefer to just type. Mm, good question, Jenny, but I think you'd need, yeah, I'm not sure actually. I don't think so, because otherwise they would have tried to implement that already. But I'm not sure, yeah. I don't know. So any more opinions on the circular motion instead? What can you think of anything that would be
Yeah,
a pro for
I have I tried about that. I know that we can put a spin, and indeed it's a product state that with space and spin multiplied, and we can put
Mhm.
the spin to rotate and find a kind of um couples with a magnetic field, and we can put the spin to rotate, and we can make the effect of the spin coupled to the magnetic field to zero, but an centrifugal aspas force appears, and I guess that I don't know, probably the Unruh effect when you rotate, there is some dynamical, I don't know, effect that so there is two Unruh effects. I don't know, it's just a try.
Oh, that's an interesting view. Um, Luis also mentioned um, in the group chat that you do not need as much acceleration as in the linear case. You're saying that you don't need as much acceleration to observe the effect, meaning it's easier to observe for a smaller acceleration. That's the point. Okay, I guess maybe some pro would be also that, well, you can, oh, wait, let me see. Yeah, I guess one good thing would be that you can perform this experiment in some finite size lab, right? Because otherwise, how are you going to do just this huge acceleration for arbitrarily long time if this acceleration is linear, right? That would be a problem. But any more takes on that? Okay, I guess now you guys are quiet already. Um, okay, so if you guys don't want to um, keep talking, let's just have some observations. Yeah, I guess one possible way of implementing would be in a synchrotron. Yeah, that is true. So let's just type some comments of about this. So we have a clear advantage, which is that we can implement this in a lab, right? Trajectory can remain in a finite size lab for arbitrarily long times. But let's just have a small look into the math here. So let's consider here again the massless case. Okay, so massless scalar field. And I'm gonna choose the 3 plus 1D again. Okay, and we are in the vacuum. And now I will couple this to this detector that is in some circular motion. Okay, with at a radius I will denote by r and some angular velocity omega. Okay, so the trajectory of this detector is going to be simply omega tau, and then one of the directions could be our cosine of omega of gamma omega tau, then another direction is going to be the sine. And then I'll just, the other one is going to just be fixed, so I can put a 0 here. Okay. Now, okay, maybe just say that the condition is that v, the orbital velocity, has to be smaller than one, right? So it's smaller than the speed of light. And then gamma, just as a reminder, is going to be 1 minus v squared. Okay, now if we use the Weidmann function that we computed yesterday and plug in this trajectory, what we're going to find is that for the circular case, again, massless, n equals to 4. What we get is going to be minus 1 over 4 pi squared, and then we are going to get a 1 omega square tau minus tau prime minus I epsilon square minus 4 r square sine square of gamma omega tau minus tau prime minus I epsilon over 2. Okay, so this is how it looks. So maybe let's just, as a reminder, the thermal Weidman. Let me just write the thermal Weidman here, which was also for massless case and n equals to 4. U was this limit here, 1 4 b squared beta squared. Um, okay, so I mean, at this level, obviously the two Weidman functions do not match. But I remember that yesterday I mentioned to you that, well, there are some more general notions of thermality, and that the case that I presented to you specifically was a very nice case in which the two of them matched, right? For massless case, n equals 4, we have the two Weidman are gonna match, the one for removal effect and the one for the thermal bath. But this is not the case always, right? So let's not by now discard this possibility. But we have to, let's actually notice something nice. So both of them, both of these Weidman functions satisfy some property, which is that the Weidman of tau prime is equal to the Weidman of tau minus tau prime 0, which means that the Weidman only depends actually on the difference tau minus tau prime. Okay, so this is true for both of them, right? And actually, this is a requirement for thermality. So this property is called this property is called stationarity. Okay, and it is necessary for thermality. Let's see the whole thing. It's necessary but not sufficient for thermality. Okay, and this defined by the KMS condition. Now, the KMS condition actually requires more than this. So I'll just mention this briefly. So the KMS condition, what it requires is that the Weidmann function computed in this delta tau, which is tau minus tau prime, minus I beta, has to be the same as the Weidmann function computed in minus delta tau. Okay, and this condition is satisfied by the thermal Weidman function, of course, by the thermal Weidman, and is also satisfied by the linearly accelerated detector, uh, by the linearly accelerated, the Unruh effect one, Weidman, but not by this one. It's not satisfied by the circular motion one. And I would say check this information, right? Do not just accept, you can check this later. Okay? But now, remember also that yesterday um, I defined some condition in terms of the detector itself. So for the UDW detector, a minimal requirement for detector to thermalize to some depth of temperature T, which is 1 over beta, was a detailed balance condition, right? So let's just remind you um, the detail balance condition was the limit of T going to infinity of the probability of excitation over the probability of de-excitation in the adiabatic limit should be to the minus beta omega. Okay? Um, so first of all, for the uh, circular motion, this condition will not be satisfied. Okay? Now, one thing that is often done is consider the following. Um, if the detector satisfies the detailed balance condition, so if the detector satisfies this condition, the detailed balance condition, we can operationally define the bath temperature. So we can define the bath temperature by essentially just inverting this equation that I have here, okay? So the bath temperature is going to be defined as simply omega times the log between the probability of de-excitation over the probability of excitation, okay? And as it should, so for the thermal bath, obviously this is going to be simply 1 over beta. And for Unruh, as we saw yesterday, it's just a over 2 pi, okay? Now, suppose that we accept this temperature as an operational definition, ignoring the fact that the detailed balance condition is satisfied or not, okay? So suppose that I still apply this temperature, okay? So if I apply this operational definition of the bath temperature um, to the circular motion case. Um, we're gonna get something a bit weird. What we get is that the temperature of this bath depends on the gap of the detector, depends on omega, the gap of the detector. And that sounds really weird, no? What I'm saying here is basically that if I put two different thermometers, they will thermalize to different temperatures, which doesn't quite make sense, right? That's really, really weird. So, as you can tell by now, I guess my view is just that, well, we're not talking about a thermal bath. This is not exactly Unruh effect. So that's my take. Nevertheless, there are a lot of people in the field that defend that this is Unruh effect and that they are going to test using circular motion. So I'd say now it's a very good time to stop for questions because after that, we change the topic a lot. Any questions or opinions or divergences? Well, yes. I mean, yes, vacuum fluctuations are going to play roles everywhere here, right? But yeah, basically what the detector is measuring is like what happens is the detector can get excited and then you just measure, right? It's like this is the same discussion as we had before. Now, whether the behavior is going to be thermal or not, it's a different story, right? Um, Luis, the calculation is complicated, let's say, but if you wanna check this reference here, it's really long and complete, so I'd recommend that you check that. But it's not, they don't have a closed form expression for all possible cases. But it's interesting that they do take the limit for small gap versus large gap, and the result is different. And another way of thinking of that is also that this detailed balance condition should actually be satisfied for every level of for all possible levels. So here we're just talking about a qubit, right? But if I had a Q tree, let's say, and the gap, suppose the gap is not the same between ground and first excited state, and then between first and second. Uh, this wouldn't be able to thermalize the two transitions to the same temperature because it depends, if this temperature depends on the gap, there's no way that the final state of this Q tree is going to look like a Gibbs state, right? So we can say that, well, this won't thermalize, okay? Yes, I think the lesson here, Marcus, would be that in order to make sense to define some temperature, it should not depend on the details of the detector itself, right? It should not depend on the temperature should not depend on what is the gap of the detector. Otherwise, like what kind of bath is that that if I put one thermometer that I choose, I'm gonna find some temperature, and then you put another thermometer that you like more, you're gonna find another temperature. That doesn't really sound physical. Like, it doesn't sound like it's a thermal bath, right? A thermal bath should be such that all thermometers have to thermalize the same temperature. But that's basically the intuition here. All right. Any more questions, or should I start the next topic? Okay, if nobody is speaking, let's start. So the next topic and last topic of this course is going to be entanglement harvesting. Entanglement harvesting protocol. And I like this topic a lot because when I was in undergrad, I saw a short video by my supervisor explaining very briefly entanglement harvesting, and I was like, oh my God, this is so cool. I want to learn more about that. I want to work on this field. It was really interesting. I don't know if it sounded a bit magical at first, quote unquote magical, not really, but you see what I mean. So it was quite nice. So I hope you enjoy this topic as well. So the question that we want to address here is the following. Can initially uncorrelated probes that are in space-like separated regions, space-like, of the space-time become correlated? That is the question. Okay? Any guesses for this question? Or how they would become correlated? Well, if we think about GR, um, classical correlations, they can come from some direct or some indirect causal interaction. So it could be some direct or indirect causal interaction. Okay, so by direct, you can think, for instance, of scattering or so any classical field interaction. Now, for indirect, we can think of basically there was some interaction in their shared path like cone, right? So there was some interaction in their shared path like cone. Okay, but here we're assuming that the two probes are initially uncorrelated. So this is not the case here. Okay. Because they are initially uncorrelated, right? So, well, what we can conclude is that two systems that are initially uncorrelated cannot become classically correlated without some sort of causal contact. Okay. Now, what does quantum mechanics tells us? Okay, so quantum mechanics is going to tell us that if you take a lattice of coupled harmonic oscillators, or a quantum field, which is pretty much the same, but taking the limit of infinite many harmonic oscillators that are infinitely close to each other. So both of them are such that they can be in a state that has entanglement between space-like separated regions. Okay, so actually a fun fact is that the vacuum is one of those states. So the ground or the ground state, if you prefer, is one of the states. So it has this property. Okay, which is quite nice, right? Now, so what we can conclude here is that two systems, they are initially uncorrelated. They can become entangled um, with one another if they can locally interact with a quantum field. And that's true even if they are unable to communicate. Okay, so what the entanglement harvesting is doing is just implementing this. Okay, so the entanglement harvesting protocol is going to implement this idea using particle detectors. So that is the idea. Okay. So let's look into this protocol, unless you guys have questions now. No? Okay. So let's see the setup. First of all, here we'll have 3 plus 1D flat spacetime. Okay. And now we'll add some real scalar field in the vacuum. So Minkowski vacuum. Okay. And then there's two particle detectors, right? So two initially uncorrelated particle detectors. And I'll choose both of them in their respective ground states. And on top of that, I'll say that they are uh, inertial and co-moving to simplify a little bit the math. Okay? So what is my initial state in this case? My initial state will be the rho is going to be the initial state for A, right? For detector A. Yeah, A here is going to be the first detector, B the other detector, okay? So the initial state for detector A, initial state for detector B, and then some initial state for the field, which is going to be the Minkowski vacuum, right? So if I can write this in the basis of ground and excited for the detectors, this is going to be ground ground for A, tensor ground ground for B, tensor the Minkowski vacuum. Okay, and just that. Um, just like later, I may sometimes just drop these A's and B's here just to make my life a little bit easier. But I'll always keep in the same order, okay? So the first one is going to be A, the second one is going to be B. All right. So let me write the interaction Hamiltonian in this case. Hamiltonian uh, in the interaction picture. What this is gonna be is going to be simply the Hamiltonian for A plus the Hamiltonian for B. Okay, which means that if you remember the form of each of those Hamiltonians that I said before, oh, yeah, I forgot to say that they are also point-like. So for the point-like case that I gave you the form of this Hamiltonian. I'm gonna just sum for A and B, and then we had some coupling constant, right? Then the switching function, and then the monopole moment for each of them, and then tensor product of the field in the position T, X, okay? But I will consider here that lambda A equals to lambda B, which would be true, say, if they are equal detectors, okay? So if I consider them um, to be equal, to be the same, not the same, but to be identical, exactly. So I think best word would be identical. Okay. Now, what I should write here is to help you understand more clearly. Is just rewrite the same equation, but make explicit when we're talking what's happening in the other detectors Hilbert space. So I'm just gonna write that I have some term um, that is for A. So this term that is the Hamiltonian for A. I can just tensor product here, some identity on B. Okay, so nothing's happening. And then there is this coupling with the field there. And then the same thing just for B. So I'll have the identity on A and then the monopole moment for B. and then the field operator. Okay, the field amplitude. So we need to time evolve this state, of course. So we need the Dyson expansion. So let's remind you. So that's going to be the identity plus the first contribution plus the second plus higher order, right? So uh, the first order was given by minus I integral from minus infinity to infinity of dt of the Hamiltonian. We saw this on Tuesday, remember? So just reminding you, this is going to be minus integral from minus infinity to infinity of dt minus infinity to infinity of dt prime. Oh, and then there's the heavy side, t minus t prime, right? And then the Hamiltonian on t prime, right? Now, let's remember that the first order, we discussed some calculation that was similar to this, and then we saw that the first order vanished for the vacuum, right? Because we know that the 1-point correlator for the vacuum is going to vanish. Okay, so I'm not gonna compute this again. If you remember, if you want, you can check the notes from Tuesday. So the first order will vanish, okay? Because it depends on the 1-point correlator. It depends on this for Minkowski vacuum, which is zero. Now let's try to compute the second order contributions. Okay, so let's remember that the second order contribution is going to come from, for the detector already, for both detectors, what we have is going to be the trace over the field degrees of freedom, remember? And then we're going to have some, the term that comes with U1 from each side. So U1 from one side times rho 0 U1 dagger. And then we had some term that depended on the U2, right? So either U2 acting on rho 0 and then the trace over phi for the complex conjugation of this, right? So this term. Okay, so basically we need to compute all of those. And before we do that, I'll would like to compute some auxiliary calculations to make our life easier. So let's remember the following. What was the form of the monopole operator? In that other lecture, what I tried to do was to simply write in some matricial representation, and then we just did all the math directly there. But here, because we have two detectors, it gets a little bit messier. So I rather just do the calculation using bracket notation, okay? So when we have some mu y of t, what was that again? This was given by ei omega t e g plus e to minus I omega t times g e. Okay. And in principle, for each of these monopole moments, so for detector A or detector B, I would have some gap here that depends on on which detector you're using, right? However, when you're using identical
Caroline.
detect, sorry, it was so loud.
Sorry.
Oh, sorry.
Sorry, I don't think that my mic is so loud. Sorry, there is a question in the chat.
Okay. Let me have a look. Sorry. Let me just write here that because we have identical detectors, the gap for A is also equal to the gap of B. And then I'll call this just, oh my God, okay. The first order vanishes because remember that when we expand the the field into the creation and annihilation operators, what we're gonna get is that, and you're taking the expectation value on the vacuum, right, on the Minkowski vacuum, the annihilation operator that you have is going to annihilate the vacuum to the right. And then the other term that has a creation operator, if you act with it into the bra, it's going to annihilate that as well. So the first order, I did the whole computation on Tuesday. So if you want to check that calculation, um, yeah, it should be there in your notes. Okay. Is that clear? Do you remember that this calculation? Yeah, it's just a fact of well, the Minkowski vacuum is a quasi-free state, so all the odd point functions are going to vanish actually, not only the first. But yeah, okay, no problem. So what I was saying here is that in general, this monopole moment would have a gap that depend on which detector you're choosing, but I chose identical detectors. Therefore, the gap is going to be the same. So this is, and thanks for interrupting me and pointing out that there was a question. Sorry that I felt so, I don't know. It just scared me for a second. Um, okay, so this is the monopole operator, and then I want to compute what happens when I act with it um, to the initial state of detector, which we chose to be the ground state, right? So if we do that, you have here the acting on ground. So if you're acting on this term with this, the inner product between E and G is gonna vanish. So you see that this is gonna vanish. So the only term that survives is this one, okay? So then what you get is e to the I omega t times E G. Okay. Now, uh, if I compute what is mu I of t times mu I of t prime times rho initial. Well, if I just look into what I just computed and notice that I can get this result with just swapping t and t prime, right? So here, I'll just copy the first one. So the first one is going to continue the same. And then this is going to be ei omega t prime eg, right? Now, again here. So we have E here. So the only term that is going to survive is this one, right? So what we get is e to the minus I omega t minus t prime. And then we have g, okay? And then one more case that we need to compute, which is going to be the case for mu y from one side of t, and then rho, and then mu y of t prime, okay? So again, I'll just copy the result that I had here in the very first one for this part. So I already have the ei omega t, and then eg, and if I active that on ei omega t, eg plus e minus I omega t ge. Now what happens here? We have g here, so we're gonna select that one, right? So if we select that one, we're gonna get e to the I omega. Oh, I forgot some primes, right? Primes here. So here I'm gonna have e to the I omega t minus t prime. And then I have excited. Does that make sense? Hopefully that's clear. So we're gonna start computing now these terms. And so these auxiliary calculations were just so that you guys, we can use these expressions here. So these were just auxiliary calculations, right? So let's start with the one that comes with U1 and U1. So that is going to be the trace U1, row 0, U1, dagger. So recall we're going to have something like minus I coming from one side, and then plus I coming from the other side. So the final result is going to be positive. And we're going to have some integral from minus infinity to infinity of dt. And the same for dt prime. And then I have some Hamiltonian acting here, and then the rho, and then another Hamiltonian on t prime. Okay, so I'm gonna factor out the lambda square, and I'm gonna have a bunch of terms. Okay, so I will yeah, work each of them. So let's look into this expression here. So we're gonna have this Hamiltonian like that, right? We have two terms here. So in the end, I'll have four terms, right? Because I have this acting on the left and this acting on the right as well. So let's see what would be all possible combinations of those. So let's see. I'll have a switching function on A. So let's take the term that comes from A and A on each side, okay? Then I'll get a mu A here, and then I have the row A, and I get the mu A of t prime on the other side. And for B, nothing happens, okay, for this case. For B, it's just the same thing. Now, we have a similar term for B. Okay, so in that case, row A doesn't change. And then we have mu B of t, mu B of t prime, right? And now we're going to have the cross terms. So the cross terms would be chi A of t, chi B of t prime. And then I'm going to act with A on the left, so mu A of t times rho 0A. And then I have B, but B is going to act on the right. So I have rho 0B, mu B of T prime. And then the other term that I'm missing, which is going to be Q chi A of T prime, chi B of T. And then I'm basically swapping the positions with respect to the previous line, right? So I have rho 0A with mu A of T prime. And then I have mu B of T and rho 0B. And of course, all of those terms would come with this trace of rho of x. Then I had the state of the field, right? The initial state of the field. And then phi x prime on the other side. And as a reminder, I can just change the order here using cyclicity. So that is just trace of rho 0 phi x prime times phi of x. And this is the Wyman function, but computed on T prime T. The order is the opposite of what we generally use. So remember that when I did the same computation on Tuesday, I ended up swapping the order of T and T prime. So that is something that I would like to do as well. But first, let's just expand this a little bit more using the auxiliary results. Well, what's happening? Well, what's happening? Oh, okay. That's weird. Sorry, guys. Technical issues. It's weird. Oh, maybe you just close the app and then open it up again. Let's see if now works. Oh, yeah. Good. Okay. So let's just use this auxiliary calculations to continue our equation. So the first one, I'll just copy this chi's, right? So chi A of T, chi A of T prime. And then I'll just copy whatever I found for this term here, okay? So mu A of T, rho mu A of T prime. So what did we have here? We had something like this, right? That's the result that we get. So we can just copy this. And so we're gonna find uh, this term for A, and then for B, nothing happens. So for B, I just have ground, as in the beginning, right? And then, well, for the second term, it's pretty much the same thing, but things are happening in B as opposed to A, right? So I already know that this is going to be chi B of T prime. And then I'll have a term that is exactly like this, e to the I omega T minus T prime. And then, but the excited should be on the B, right? And nothing happens on A. So this is what happens. This is the result. Okay. Now let's see the next one. So for the next one, we have chi A of T, chi B of T prime. And I'm acting for A is going to be mu times rho, right? Mu times rho. This is what we have, right? So that's the result for mu times rho. So that is for A. Now what's happening for B? For B is going to be rho times mu. So rho times mu is just mu times rho, but Hermitian conjugate, right? So what we're going to get here is going to be e to the minus I omega t prime, right? Times g e. Okay, so just to make my life nicer, I'll just write this together instead. So I omega t minus t prime. And then I get those terms there. And I erase here. All right. And then for the final term, if you notice, is pretty much the same thing as this one. But we're just going to, yeah, inverse the row of A and B, right? So we have whatever we had for B here, we have for A there, and whatever we have for A, we have for B now. So what is going to happen is going to be just swapping the sign here. Yes. And then swapping this. So this is E, G, right? Okay, so this is the final expression times, oh, I forgot to write the Weidman, so let me write the Weidman here. Weidman of T prime T, okay? If you're copying, don't forget to add this Weidman function here. Okay, so after all of this, I'll finally swap the T and T prime. So to do that, well, it's going to be pretty much the same thing, but let me see. This is going to be the same, the same. Then I swap the T and T prime, okay? So if I do that on the other terms, first term, the chi's don't care about that, but the exponential is going to flip sign, right? So we have minus I omega t minus t prime, and then the rest doesn't change. Now for the other ones, same here. The chi's don't change, but we change sign here. And then G, G, E, E. And then here they change. So chi A of T, chi B of T prime. And I also change the sign. Minus I, T minus T prime. And E, G, G, E. And similarly here, I'll have, no, chi A of T, right? Wait, what did I do? Yeah. So I think I forgot to swap the order here, right? You guys should tell me when I make a typo. So this is going to be chi of T prime and then T here. Yes. And then change the sign. Yes. Okay. So here is going to be of T, then T prime here, and then E I omega T minus T prime. Okay. So now it's already in the order that I like. So we can just save this result. Okay. Any questions here? It's just calculations, right? Just tedious calculations, but they are necessary. So let's do now the other contribution. So we want the contribution from trace acting with U2 and rho 0. Okay, so here we're gonna get a minus lambda square integral from minus infinity to infinity. Just repeating what we have, okay? Just going to be this times the Hamiltonian and T prime. And then we have to act with this on rho 0, right? In the initial state. So let's see. Oh, let me just. Oh, this should not be this. Yeah, here. I already jumped ahead. So dt prime um, of the heavy side. And then let's see what else do we get. So we're gonna have always acting with these monopole operators um, only coming from the left, right? That's but by the way that we wrote the Hamiltonian acting from the left. So let's see, we get chi A. Now the AA term again. Then we have mu A and T prime. And then the initial state for A. And then nothing happens on B, right? And then the same idea, but for B, so chi of B, chi B of T prime. And then I have just rho 0A. And then I have mu acting on B. And now we're going to have the cross terms. So chi A of T, chi B of T prime. And then I'm going to get just mu A of T acting on rho A. And then mu B of T prime acting on rho B. And finally, chi A of T prime, chi B of T. And same as before, but on T prime. And then this is going to be on T, rho AB. All right. And all of that still need to be multiplied by the trace of phi on x prime, and then the initial state of the field. Okay. So this is already in the order that I like, actually, right? Meaning if I do use cyclicity, I can write as this, which is my Weidmann function in the order that I like. Oh, this is ugly. The Weidmann function on T prime. Okay. Now let's just rewrite this same as before, making it more explicit. So this is going to be minus lambda square times the integral from minus infinity to infinity of dt prime as well. Then I have the heavy side and the Weidmann on t prime. Okay, I already wrote the Weidmann there. So let's plug in the terms here. So we have chi of t, chi of t prime. Let me open more space. And then in this case here, I have mu acting on rho, right? Let's see what we had for this. Mu acting on rho. This is going to give us this result here. Let's copy it. So we have this for A, and then nothing happens for B, right? Okay. And remember that the second term is pretty much the same idea, but on B instead of A. So we have rho B of T prime. And then, well, the same factor, right? E to the minus I omega T minus T prime. Even though it's acting there, both of them are just GG, so it doesn't matter. And then the cross terms. So let's see the cross term. First one I have chi of T, chi B of T prime. And then I'll act with mu times rho. So mu times rho was something like this. So we have mu times rho for A. And then we have the same thing, but on T prime for B, right? So it's going to be the same thing on T prime. And then if I just factor out these exponentials, I'll get that E I omega T plus T prime. Okay. Um, and then finally the last one here is going to be chi B, chi A of T prime, chi B of T. And then I have exactly the same things, but here instead of, I'll just basically have to swap T and T prime, right? But if I swap, nothing really happens here. So I just have the same thing for this exponential, right? And then I'll get the same state here. Okay. And this one is already on the order that I like, so I don't need to do anything else. Let's see the last one. So the last one, remember that we have trace of row 0, you add 2 dagger. So we can just basically do the same thing. Basically, we already did this computation, right? So if we look into this, now we just have to take the complex conjugate um, inside. So this is going to give us, let me write down, minus lambda square. So the integrals are now going to change. The heavy side is still the same. The Weidman is going to change. Let me just put in another color so you guys notice. So this is going to swap, okay? Because the Weidman, the conjugate of the Weidman is just swapping the arguments. And then what we have for the other parts, we have to take the complex, the Hermitian conjugate, right? So if I have this, oh, you get positive now, right? So I had positive here, and then conjugate here is just the same. Now, same for B. This is going to be plus omega T minus T prime. And then we have GG, GG. And now for the other ones, I have then I'll get a pick a minus sign here. And then do the Hermitian conjugate. So this is going to be G, E, G, E. Okay. And then same for the other one. Negative here. times GEG. Okay, so now there's only one more step, which is swapping the order of T and T prime so that I have the order that I like. So let's do that. So it's pretty much the same thing that we have, right? But let's just swap the orders here. So this is going to be dt, t prime. So the heavy side here, remember, is going to change the position. So here, let me just write down what we're doing. T and t prime. So here is going to be t prime minus t, okay? And the Weidman also changes for the order that I like. And then, wow, in the first term, we just had Ka of t, Ka of t prime, so nothing changed for this part. But now that we're swapping on the exponential, that's the same as taking the Hermitian conjugate, the complex conjugate, right? So t minus t prime. And then we just have GG. Then for same for B, right? This part is invariant. Now we're gonna get something that is also negative here from what it was before. GG, GG. And let's see. So now we have, we're gonna change for chi A of t prime, chi B of t, and then swap the signs, right? Oh no, we don't swap the sign because if we have, since both of them have the same sign, if we swap t and t prime, it's just the same thing. So we have minus I omega t plus t prime times GEG, and the same for the other one. So uh, t and t prime. Okay, now we're pretty much done with this calculation. Okay, so we should collect it, all of these terms. So we need to, um, basically, I'll leave this as an exercise for you guys, but you just have to focus on, oh, what are all the terms that depend on GG, and then you sum all of them, manipulate, use some of the properties of heavy sides of X plus heavy side of minus X being 1 in some situations. And then if you collect all of them, so collecting all terms uh, in a matrix, uh, we get the final state for both detectors. So what would be this? This matrix is, it should be row final of the detectors of for A and B. This is going to give us 1 minus L AA minus L BB. Then we have a 0, and then M. Then we have 0, LAA, LAB star, 0, 0, LAB here. Then LBB, 0, M star, 0, 0, 0. All of this plus order lambda 4. Because as I said, that lambda cubed is going to vanish. Okay, all the odd point functions vanish. Um, and maybe I have to write that the basis, the order of the basis, right, is GG. Okay, so here I'm implicitly assuming that you know that there's a tensor product between those. So I have GG, EG, GE, and EE. That is the basis, the order of the basis that I chose. And let's define what is each of those terms, right? So we have the LAA, it's going to be lambda square integral from minus infinity to infinity of dt, also of dt prime, Ka of t prime. And then I have e to the minus I, omega t minus t prime times my Weidman. And pretty much the same is true for B. So if I have LBB instead, it's going to be the same thing, but for B. Okay. Chi B. Now LAB are going to, it's going to be lambda square dt dt prime Ka of t, Kb of t prime, and then e to the I omega t minus t prime times the Weidman, and finally the m term. The m term is going to be minus lambda square integral from minus infinity to infinity of dt of dt prime. Then we have the heavy side, okay, and then chi a of t, chi b of t prime plus chi a of t prime, chi b of t, everything times e to the I omega t plus t prime times the Weidman. Okay, so these are all the terms. And if you look into this this matrix, basically what we have here are the, so this is the excitation probability for A. This is the excitation probability for B. And okay, so they appear here as well. And now the off-diagonal terms, these ones, they are the coherences of our matrices, right? Coherences. Okay. Now, well, we started with a state that was a separable state, right? We had just ground for the first detector, ground for the second detector. And I'm defining some protocol that is called entanglement harvesting. So I should tell you, I should show to you that we actually harvested some entanglement, right? So what we should see is that the final state of this detector had some entanglement, right? Because the initial one didn't have any, right? Um, so any questions before I look into that? All right, so let's see the following. We need to, we need a way to measure the entanglement between the detectors A and B, right? So, um, first of all, what we have is that in general, the final state of the detector after of the two detectors after interacting with the field is going to be some mixed state, okay? So in general, this row AB is a mixed state. And when I talk about measuring entanglement, most people, at least if they are more from some high energy background, what they'll tell me is that, oh, I want to measure entanglement, let's use entanglement entropy. But when we have mixed states, we cannot use entanglement entropy because for mixed states, entanglement entropy is not a proper measure of entanglement. So you'd be wrong to use entanglement entropy here. We cannot use entanglement entropy. Okay, so now for mixed states, in general, the problem of finding whether a state is entangled or not is really, really hard. So given um, uh, given some mixed density matrix, there's a question. Yes, exactly. Let's see the questions just a second. Pedro, yes, you can think of that as because basically to see entanglement, we generally well, how we use entanglement entropy to measure entanglement is we take the entanglement entropy of the state of the two detectors, let's say, of the two parties, and then we compute the entanglement entropy for those and then trace out one of them and see if that entanglement entropy increase or not. But if you already started with a mixed state, let's say you start with the maximally mixed state, your initial state is already has non-zero entanglement entropy already. So it's not going to be a proper measure in that case. So as you said, I think, yeah, you can think of that as mixing the two indeterminacies. Now, let's see. Um, well, Marcus, I think the definition of entanglement would be a state is entangled if it's not separable. That is the only good definition of entanglement, right? It's hard to, you cannot really circumvent this definition. Um, I agree with you that it's not that easy, but precisely because of that, that is hard to tell whether a state is entangled or not. So, given a mixed density matrix, what we know, let's see, for a bipartite state, deciding whether it is separable or entangled is actually an NP-hard problem. So in general, this would be really, really hard. Okay? There's no good solution to tell whether some state is entangled or separable. But the good thing about the detectors, especially for the qubit ones, however, um, in our case, when we have just two qubits, uh, there is one proper measure of entanglement. that is easy to compute. So the negativity, actually it's proportional to concurrence. There are other measures as well, but the important thing is that if we just have two qubits, that is an easy task, okay? So the negativity is a proper measure. The negativity is the one that I'm gonna choose here. So it's a proper measure of entanglement. This would also be true if I had chosen one detector that is a qubit and another detector that is a qubit. But if I had, for instance, two qubits, then negativity would not be a proper measure of entanglement already. So the situation gets complicated very quickly. So let me tell you what is the negativity, right? So the negativity of some density matrix is going to be given by okay, let me just write it down and then explain what this notation means. Okay, just okay. Okay, so that is the formula for negativity. And then what is each of these things, right? This thing here, this notation here, um, is the partial transpose of rho, okay? And this is just the trace norm. So the trace norm, let me put here. The trace norm is going to be given like this. The trace norm of x is just going to be the trace of the square root of x dagger x, okay? Now, if someone has ever heard about this Perez-Horodecky criterion, negativity comes from that. So this idea of having a partial transpose comes from the Perez-Horodecky criterion to determine whether a state is separable or not. So um, let's just also understand what is a partial transpose maybe, right? So let's just illustrate this a little bit. So there's the partial transpose. Let's say that you're acting with, um, take the partial transpose with respect to the second system, okay? So suppose that we can write rho like this, so I can have this four part here. So what is going to be is going to be, I take the partial transpose in each of these blocks. So I take the transpose in each of these blocks. Okay, that is equivalent to taking the partial transpose with respect to the second system. So basically we transpose within each of these blocks. Okay. Now, if I want to compute instead the partial transpose with respect to the first system, then what I'm going to do is simply swap these two blocks. So I'm gonna swap this block up and put this one down here. Okay, transpose. So this means that I'm transposing um, each block themselves. So I'm transposing the actual block. Okay, so that was somewhat of a detour, but if we compute negativity in our case, so for that density matrix that I presented to you guys, what I see is that the negativity of this detector, the final state of the detector, is going to be the minimum between 0.5 of the square root of LAA minus LBB squared plus 4m squared minus LAA minus LBB, and then plus higher order corrections, of course. Okay, now I mentioned to you guys that um, we're thinking about two identical detectors. So in the case of two identical detectors, this simplifies further, and then what we're going to get is that the negativity of this state is going to be the minimum between 0 and n minus LAA, which is the same as LAB, right? Plus higher order corrections. Um, so you can think of this answer as some sort of fight, right, between M and LAA. So you'd say that this LAA has which is just the excitation probability for each of these detectors, would act somewhat as a noise, right? Trying to uh, just like compete against the term that is driving this entanglement. So in some sense, M is responsible for this entanglement, and LAA is just the local noise that is hindering the harvesting of more entanglement. Um, Now, one thing that I thought of discussing is remember that I mentioned that this reference in the beginning, there's a very nice reference that discusses the entanglement harvesting for a few cases. And I thought, let me see, I had copied somewhere. Okay, here. So from that reference, I copied this plot that they made, which was for Gaussian switchings. So the idea that they did here was basically um, okay, separating these two point-like detectors. Okay, so I have a point-like detector in some position, a point-like detector in another position. So this D here in this plot, maybe I should zoom in. This here, D here in this plot is going to give you the separation between the two detectors, okay? And here I basically have um, the detector gap, okay? And then and here's a time delay. This time delay means that they turned on one of the Gaussian switchings and then waited for some time, which they fix here, and then turn on the other one, okay? And and then here is basically because they have Gaussian switchings. If you think about they have support everywhere, right? Like a Gaussian has support everywhere. So you have to have an idea of what would be the region of strong support of this Gaussian. So they try to determine in which situation or uh, starting from which point that we can say safely that these two detectors are in space-like separation, okay? So for the setup that they chose here, they drew this dotted line to represent where they are sufficiently space-like separated. And if you notice the way that they plotted here, you can have there's some relation between the gap that you need in order to harvest when we have a larger separation, right? So what it's saying here, if you notice this behavior, is that the larger the two detectors are, the larger is the gap that you need in order to harvest entanglement. And the intuition here is that, well, if you have a very small gap, then you're going to have a lot of this probability of excitation. It's much easier to excite this detector. So the local noise is going to be big enough that it's going to kill the negativity. The M term cannot compete with this LAA. Now, maybe I should say that the white part is the part that has no entanglement, and the red one is the part that has entanglement. Okay, so you see that if you have a larger separation, you need a higher gap in order to harvest entanglement. But in any case, you can see that even in regions that are sufficiently space-like separated, we can still harvest entanglement from the vacuum. I'd also highly recommend that you have a look into this reference. In general, they also discuss other cases. I found easier to just focus on the point-like detectors, but they consider Gaussian switching and Gaussian spatial smearing as well. Then this case that I showed to you, which is Gaussian switching and point-like detectors, and they also consider some cases in which you have a sudden switching, so it's on, like you just turn on non-adiabatically and leave it on for a while and then turn it off non-adiabatically as well. And I think in that case they also take the limit of point-like detectors, but they don't start from point-like detectors. They take the limit afterwards so that things converge nicely. But I guess that's it. And if you have more questions regarding entanglement harvesting, I hope that you found this protocol cool. I find it very cool. And yes, I think that was what I had planned for this course. I hope you have enjoyed it. And again, feel free to ask me questions now or later by email. Thank you so much for attending.